So welcome. So here we're talking about frictional forces. We touched on this last time. And what we decided was we can divide the friction world up into two kind of parts. We can divide it up into the static part and the kinetic part. And in this, whereas with statics and dynamics, it's not about motion or non-motion, it's about acceleration or no acceleration. In this, it is about motion. In this, it literally is about motion. And so what we found is we can characterize our amount of friction by these coefficients of friction. There's one for static friction, there's one for kinetic friction. And there's a kind of weird thing about the static friction in that before I'm moving, you know, the amount of friction can be, if I don't apply much, I don't get as much. So it's not equal to this factor times the normal force. It's equal or less than this factor times the normal force. If I only push with a little bit, I only get a little bit of friction. If I push with a little bit more, I get a little bit more friction, and so on, until I get to this point of slipping. And that's the equals bit. So when I say FF is equal to mu s times Fn, that's what I'm working out, that amount of friction there. And because the coefficient of static friction tends to be a little bit more than the coefficient of kinetic friction, when I'm moving, I have a slightly lower frictional value. And it's constant, doesn't matter how fast I'm moving, within reason. If I'm going, you know, incredibly fast, I'm sure other things happen, but within reason. So I have these two things. I use the normal force rather than the frictional force because I'd like to have a force that tells me the degree of enmeshment. I shouldn't do it like that. And the degree of enmeshment is the force that's perpendicular to the actual interface, and so that would be the normal force. The weight is not always perpendicular to the surface, whereas the normal force is. So it's better to use the normal force. So I think we did this last time, but we'll just flip through it. A 2 kilogram block sits on a level table, so here's my 2 kilogram block. I put the 2 inside the block. There is a 0.4 coefficient of static friction, so it's stationary. What is the maximum force of friction that can be produced? Well, let's just visualize a system. We have an applied force, and then we have a frictional force. It's not that the frictional force exists even if I'm not pushing. It's that the frictional force exists in response to my pushing. And I try and solve this in one step, and I say, well, hold on. FF is equal to, is less than or equal to mu s times Fn. And maximum force means I'm at my point of slipping. So for the maximum force, that's going to be equal to mu s times Fn. And then I plug in what I know. So this is going to be 0.4, and the problem is I don't know my Fn. Oh man, if only I knew my Fn. So I look back and I go, well, hold on. I've got my Fg here, and I've got my Fn there. Oh, the sum of the forces vertically equals 0. So that means that plus Fn added to minus Fg is equal to 0. So that means that Fn is equal to Fg, and Fg I know always equals mg, because it's, you know, W equals mg, which equals 2 times 10, which equals 20 newtons. Oh, that was okay. And then I say, well, in that case, FF is equal to 0.4 times 20, which equals 8 newtons. I'm being a little bit pedantic there. I'm kind of taking you through it step by step. But in principle, that's what you do. In reality, a lot of people will just recognize that Fn is the opposite to Fg, and they'll say, well, the weight is 20. I can just do that. 2 times 10 is 20. So it'll know that Fn equals 20 just by observation. And I think sometimes the problem is they're not really aware of everything they're doing. And the problem is if I give you a slightly more complicated problem where now Fn is there and now Fg is there, now you can't just look at it and say, oh yeah, if the weight is 20, the Fn is 20, because that's not true anymore. So in principle, you should be trying to find Fn using Newton's laws. It seems a little bit, you know, like deliberately going slowly for this problem. But when a more complicated problem comes, you're going to use the same technique. Which trace best represents the relationship between frictional force and normal force? So I want to introduce a couple of new skills. Remember we talk about this course in terms of its content and its skills. I want to introduce a couple of new skills. And one of them is about being able to go from equations to graphs and backwards and forwards. And the other one is about being able to get an answer when I just give you a ratio of changes. So any equation, I can do it as a numerical problem. I can do it as a graphical problem. I can do it as a ratio problem. And so I tend to mix those up a bit. But I want to introduce that skill here. So if I look at this, I say, well, okay, then we have basically an expression that links the frictional force and the normal force. Oh, yeah, okay. And this is for a moving object. So I say, well, Ff is equal to mu k times Fn. And mu k is about the interface. So it doesn't change. The object moves across the tabletop. It's the same interface. So mu k is constant for any given visualization. Can anybody look at that and tell me what's the name of that type of relationship? Is it a linear relationship? Is it inverse? Is it quadratic? What kind of relationship is it? Can you just spot it? It's linear. Some people can just spot it. For others, we got to work it a bit. And so to some extent, what other people have to do is they have to turn around and say, well, that's a constant, so let's call that 1. So Ff is equal to 1 times Fn, and some people will get it at that point. And then for other people, you've got to go, well, let's have a look. Linear would be y equals the slope. I don't use m because m means mass very often. Y equals slope x plus b. Oh yeah, that looks like that. The y-axis is my Ff, and the x-axis is my Fn. So yeah, y is equal to some constant times x plus b. So it's linear. Yeah. So in a whole bunch of ways you can get it linear. If that doesn't work, then what you do is you just turn around and you say, well, let's have a look. I want to plot Ff and I want to plot Fn. And any constant, say mu k, is going to equal 1. Why not? It's a constant. Who cares? You can't make it 0, or else you lose the expression because you just cancelled it all out. But why not make it 1? And then I go, well, if Fn is 0 or 1 or 2 or 3 or 4 or 5, well, 1 times 0 is 0, and 1 times 1 is 1, and 1 times 2 is 2, and 1 times 3 is 3, and 1 times 4 is 4, and 1 times 5 is 5. And you can even go to that next stage where you say, well, that's 0 and that's 0, and that's Ff and that's Fn. And then you go 1, 2, 3, 4, 5. And then you go 1, 2, 3, 4, 5. Then you go 1 and 1, and 2 and 2, and 3 and 3, and 4 and 4, and 5 and 5. And I think by that stage you can say it's linear. So maybe you'll see it from the equation. Maybe you'll see it from the equation with a little bit of manipulation. Or maybe you've got to actually do the table and figure it out. So on this example, which one would it be? Would it be trace A, trace B, trace C, trace D, or trace E? It's going to be D, isn't it? The B is also linear, but it's going the wrong way. It's going to be trace D. And that's the skill. Now, eventually, I'm going to not give you this. I'm simply going to give you the axes with a whole bunch of grid lines on and no numbers anywhere. And I'm going to say, plot me the graph. And often people start by saying, well, which numbers shall I use? And I'm going to turn around and say, I don't care. And then you got to pick. And so the skill is on me. I got to be able to, if you use 1, 2, 3, 4, 5, or 5, 10, 15, 20, 25, or 1,000, 2,000, 3,000, 4,000, 5,000, or, you know, 0.1, 0.2, 0.3, 0.4. I got to be able to figure out if your graph's right. And I can. Because the actual numbers don't matter. It's the ratios between the numbers. That makes people feel very uncomfortable when I don't actually give you a number. It just makes people, it's like, where do I begin? Because you've never been trained to do it. You've always been trained to complete this table or do this experiment and go from here to here. But you've never been given free rein to kind of just say, okay, I'm going to go from 0 to 7 and see how it goes. And so that freaks some people out, but it's only just experience. That's the second level skill. The first level skill, which we'll deal with for a while, is can you pick out the actual trace? And the second level skill will then be, well, okay, can you actually draw me a graph? And put numbers on, etc. So we'll practice that and I'll train you in that. But for the moment, not for this first test, but for the second test, there'll be some kind of graphical thing. Might not be on this equation, could be on any of the equations we've used. Which is the graph that best suits it? So, which is the trace that best suits it? That's one skill. Then the next skill we're going to practice is where you know the answer under the current conditions. What's the answer going to be if I twist that knob so it's twice as big and make that one a third as big, make that one 7 times as big? I don't tell you what the numbers are, I just tell you the changes in the numbers, because that's often what you're faced with. And this is a ratio problem. So this says a block slides across a level table. The force of friction between the block and the table is 6 newtons. So let's put our FF there. And that equals 6 newtons. And then it says, what is the new coefficient of friction? What is the new friction force if the mass of the block is tripled and the coefficient of kinetic friction is quadrupled? So I'm going to have a bigger mass. And it's not only that, it's going to be on a different table because we have a different coefficient of friction. Now what's the friction force? It's like, whoa, you're changing everything. How can I do this? It's a ratio. So the first skill is you've got to know the equation. So you've got to know that FF is equal to mu k times Fn. You've got to know that. And then the rest is you're going to do a new version of it versus the old version of it. And the new version is what you want. That's my advice. You can do it any way you like, but the new version is what you want. So I say, well, I want my FF, and I want the new version of it. And I'm going to compare that as a ratio with my FF, the old version of it. And you go, well, hold on. I don't know the new value, but I do know the old value. The old value is 6. So then how do we get this? Well, it's going to be the new value of mu k over the new value of the normal force. 2 n's there is always a little bit unfortunate. Over the old value of mu k times the old value of the normal force. Now, I don't know the new value of mu k, and I don't know the old value of mu k, but I do know that the coefficient of kinetic friction is quadrupled. So it's 4 times bigger. Well, the easiest way to do that is call the old one 1 and the new one 4. Supposing that you didn't have that insight, supposing you said, well, I'm going to call the old one 1/4 and the new one 1, it still works. If I'd called the old one 5 and the new one 20, it still works. You could call it 1 mu k and 4 mu k's. You can leave the letter in if you want, as long as you're going to cancel the letter out. As long as the ratio is 1 to 4, you've done what the question says. And then we have our Fn, and we know that the mass of the block is tripled. Not Fn, but the mass of the block is tripled. Now we're going to do a bit of conceptual stuff. Well, there's my mg, and there's my Fn. And I am on the level. I'm on a flat surface. So I can look, and I can say Fn is just equal in size to mg. That's how it works, yeah? Sum of the, if you like, formally, the sum of the forces vertically equals 0, so plus Fn plus minus Fg equals 0, so Fn equals Fg, which equals mg, which equals the mass times 10, yeah? That's how we get it, yeah? But I can see that, and I can say, oh, so this would be, so I'm gonna sorry if you've written that last bit down, I'm gonna just backtrack a little bit. I'm gonna get rid of that. I'm gonna come down here. I'm gonna say, well, this is equal to mu k nu, not times Fn nu, but m nu g. And this is mu k old, not times Fn old, but m old g. And if I like, I can have new g and old g, like I'm going to different planets. Doesn't matter. Now I can put my numbers in. Simplest ratio for that is 4 to 1. For the masses is triple, so the new mass is 3 times bigger than the old mass. And it doesn't even mention g. We don't go talking about going to a new planet. So let's call it, if you want, 9.8 over 9.8, if that helps. But it's just going to be 1 over 1 as far as the same ratio. And that equals 12. And a whole bunch of people, the first time they do this, will tell me that the new frictional force is 12 newtons. But it's not. Because the new frictional force over 6 is equal to 12. So the new frictional force is equal to 12 times 6, which equals to 72 newtons. And I can pretty well guarantee, when somebody gives me the answer of 12 for that they're not writing in equations. They're not saying FF new over FF old equals FF new over 6, which equals mu k new times Fn new over mu k old times Fn old. They're kind of doing all this stuff in their head. And they're going, well, let's see, there's a ratio of 4 to 1, and there's a ratio of 3 to 1, so that's 12. And so they write down 12. And because they're not thinking in sentences, they're not mindful of the fact it's FF new over 6 equals this ratio. And we're forever trying to train you to think in sentences, to think in equations. And so this is an example where if you're not thinking in equations, not every time, but more often than you need to, you'll make that slip and just think in terms of the ratio. This strikes me like the factor label technique, where factor labels, you know it's about ratios of things, but man, it's easy to get them backwards. So you have that formalism, that layout that prevents you from getting them backwards. This is a similar idea where it's easy to get these backwards. We know it's some ratio, but if you lay it out, then you'll just float through it. It becomes very easy when you lay it out. When you don't lay it out, it becomes a little bit confusing. We got some. I know. I mean, every class. This is. I think the wonderful thing about HCC and America actually is we have people from all over the world, and so not everybody was like me. Was raised with English, And if it's a technical term, if you say to me, oh, I don't know what momentum is, I'm going to turn around and say, well, read the book because it's in there. But there's other times when it's a colloquialism or it's just a terminology that you might just skip. I remember at USF, I had a student who had never heard the term seesaw. She was Japanese. She'd never heard the term seesaw. If you don't have kids, you're not gonna know the term seesaw. I doubt they do it in, in the Rosetta Stone. I doubt it has seesaw in it. It's like you don't learn that. She shouldn't not be able to do the problem because she don't know this colloquialism. So I'll gladly answer a question like that. And I kind of feel the same way about quadrupled and stuff like that, because quadrupled is a bit like quartered, and I can see how you get that confused. If you ask me about momentum, you're on your own. But if you ask me about something like that, I will gladly answer it. I think that's fair enough. I don't want to not use it and say 4 times as much. But, I understand. So the third skill we've added, really, So this next bit, statistics with friction. So horizontal forces applied. A force of 8 newtons causes a 2 kilogram block to slide at a steady speed of 7 meters per second across a level table. I need to start bringing the clickers so you can have a go at these. Let's have a look. Horizontal force of 8 newtons. Let's do F applied equals 8 newtons. 2 kilogram block. I always put my masses inside the block. I always put my forces at the end of arrows, kind of in line with the block. I put my velocities kind of like an arrows parallel to the block. So, slides at a steady distance of, that's going to be 7 meters per second. Level table. What's the coefficient of friction? Whoa. Is that it? Let's put down mu. It's moving, so it's mu k equals, I don't know. Let's change coloured pen so we can see the thinking process. Well, my diagram's not complete. I know that. So with these, it's a good idea to finish your diagram off. I know there's going to be a weight. And of course, I know there is a frictional force. That's what I want to find. And I know that whenever you get, a block on a table, there's going to be a normal force. I think that's all the forces. And then I say, okay, let's try and solve this. FF is equal to mu k times Fn. I want to find mu k. Mu k is equal to FF over Fn. Okay. Find FF. Find FF using FF is a horizontal thing. I'm going to say the sum of the forces horizontally equals 0. Why is it 0? Steady speed. Yeah. That's why it's 0. No acceleration. Even though it's moving, there's no acceleration. So I say, okay, plus FA added to minus FF equals 0. Fn has no component because it's at 90 degrees. And weight has no component because it's at 90 degrees. So ignore them. FF is equal to FA. And FA is equal to 8 newtons. So FF is equal to 8 newtons. That's part of it done. Find Fn using, well, Fn is a vertical thing, so let's say the sum of the forces vertically equals 0. Why is it not accelerating? Because it's not rising up in the air faster and faster. It's not descending into the earth faster and faster. It's just traveling on a level table, so no acceleration vertically. I look at my diagram and I say Fn, which is in the positive direction, added to minus Fg, minus because it's in the negative direction, equals 0. So Fn is equal to Fg. And Fg, of course, is equal to the weight, which equals mg. So that g is a subscript and this g is the thing in its own right. So let's put that in brackets so we don't get those two things confused. And that equals m, which is 2, times g, which is 10. So Fn equals 20 newtons. And I know with practice people will look and say, oh yeah, that equals 20, so that equals 20. And if you put down a line saying, you know, Fn and Fg are equal and opposite, so Fn equals 20, I know you know what you're doing, you know. If you put down Fn equals 20 newtons, I'm pretty certain you know what you're doing if you've got other work. If you've got a blank sheet of paper and you just put down mu is equal to, then I got an issue. But if you're putting work down, if you skip steps, it's your choice. I'm not saying I'll never skip that step, you know, but I'm aware that when I skip steps, I'm a bit more likely to make a bit of a break. And so this, bring that up there, and bring that up there. That is equal to 8 over 20, which equals 0.4. What are the units going to be? Don't want to miss my units. What are the units going to be? There is no units, yeah. There is no units. This is, look at your equation. If you don't know the units, always look at the thing and say, well, it's newtons over newtons, so there's no units. Okay. Not bad. It's just a bit long. That's okay. Let's make it a bit more interesting. 3 kilogram block is stationary, but now it's on a slope. Try and draw your diagram to scale. You know, you got time, if need be, get a little protractor and draw it to scale. You don't want everything at 45 degrees. It will confuse you. Little squares, not big squares. Big arrows. And that's going to be 3. So that's going to be 30 newtons. Notice I just wrote down the weight. It's like, I know what it's like. Come on. Fn. FF. How do I know that FF is pointing up the slope? Why not down the slope? Because the tendency, good word, the tendency is for this thing to want to go down the slope. The friction opposes the motion or the tendency to motion. Okay. 3 kilogram block is stationary, but on the point of slipping. Okay. What is the coefficient of static friction of the block and incline? That little bit about being on the point of slipping is significant, actually. Let's change pens so I can show my, you know, I like to kind of somewhat show my diagramming, and then I like to show, if you like, my thinking. Let's do this in red. So there's the end of that bit, for the moment anyway. And I say, well, FF is less than or equal to mu static times Fn. But on the point of slipping, on point of slipping, FF is equal to, it's as big as it can be, mu s over Fn. So this means that mu s is equal to FF over Fn. Oh man, here we go again. Fine, let's change coloured pens so you can see this little bit of thinking. find FF using the sum of the forces equals 0, because it's not accelerating, but in which direction? I could do the horizontal and vertical and have two equations because I've got two unknowns, but then I've got to find Fn as well, so that's like going to be a lot of work. I want to find FF, I don't want to find Fn. Draw your axis perpendicular to Fn. I drew my axis perpendicular to the thing that I want to ignore, because there's no shadow. If I lean it across, there's a shadow. Sun's coming down, there's a shadow. That's got a component. That's got a component. That, that has no component. So if I'm 90 degrees to the thing I'm looking at, no component. So draw an axis that's at 90 degrees to Fn, no component. Look at your diagram. That is my FF. It's its own component. Dot, 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 dot. That is my component of the weight. I know that this is 30 sine 20. I know it's in a negative direction because I'm going to make that positive and that negative. Let's just pause for a minute. Let's do a little bit of geometry. So if that's 20, then this angle up here is 70. And I could have said 30 cosine 70, because I've got the hypotenuse and I want the adjacent, and I'm using the angle in between, so it could be 30 cosine 70. But if this one up here is 70, this one down here is 20, and that's an opposite to the hypotenuse, so it's a sine of 20. They're both the same. You can put down either one, but you've got to get the right number with the right thing, you know. I say plus FF added to minus 30 sine 20 is equal to 0. So FF is equal to 30 sine 20. I'm going to leave that actually for a minute. I'm just going to leave that for a minute because I want to show you something. I could work it out as a number. It would be 30 times a number that's less than 1. No. Let's change colored pens. Let's go for something like red. I'd like to be able to find Fn. And I don't want to deal with FF. So draw a line perpendicular to FF. This is its own component. It's in the line. This guy gives me a component there. I know that this is going to be 30 cosine 20. I'm going to make that the positive end, so this is going to be negative 30 cosine 20. Let's pause for a minute. Let's look at this trig. If this down here is 20, I know that that up there is 20. I have one side of it, I want the other side of it, it's a cosine of that angle. I say find Fn using the sum of the forces equals 0. on the red line, that was on the green line, this is on the red line, I go plus Fn added to minus 30 cosine 20 equals 0. So Fn is equal to 30 cosine 20. Can you see how being able to do those components? So the first skill is, can you pick the direction? And then the second skill is, having picked that direction, can you resolve your forces? Which means, can you do components on that? And you're going to use a bit of trig. I didn't work out these numerical values because I want to show you something. So let's just go up here, and let's bring that up here. Let's bring that up here. So this equals FF, which is 30 sine 20. And this guy down here is 30 cosine 20. Well, the 30s cancel. What's a sine theta over a cosine theta? Tan 20, which equals, did I? Surely I did. Yes. So tan 20, 0.364. What are the units? No units. So, same problem in a way, but because of the changing angles, I had to use a bit more trig in this case. I had to resolve my forces. In that case, I had to resolve my forces. We're all in line, so it didn't matter. In this case, they're not in line, so I gotta work a bit harder for it. But it's skills. You learned about components in the first 4 chapters, and now we're just using components. If you cannot do components, you must address it. It's like something that's going to take away from you always. So you must address it. You cannot slide by. It comes up too many times. So if you're not confident about doing components, you need to work at it more, and you need to ask for help, because the price is just too big. Okay? Any questions on that? It's a typical question. Supposing it was accelerating down the slope. That's static. That's dynamics. So for statics, we had the 2 examples. The most common are traffic light problem and on an inclined plane, a block on an inclined plane. Moving or not moving, that's what catches people. Sometimes when it's moving, people go, oh, it's dynamics. Moving or not moving, it's statics. Now let's have a look, see how I'm doing for time. I'm getting, so I can't read that. 38, okay, not bad. Let's change a little bit. What I'm going to do, because I skipped a question, I did not do that first dynamics problem. I'm going to kind of do one now. So I'm going to just get out of here. I'm going to just discard. I'm going to, where am I? I am there. I'm going to insert new slide. Was it in that bit? Where am I? New slide. And let's go back. In the next room, I think I've told you, in the next room I can just add a page, and now here in this room I can't for some reason. Okay. So, first of all, dynamics without friction. So we'll do, I've got to go back and get a pen. We'll do dyne without friction. The most classic form of this is you have a smooth, level table. And then the string travels over a massless, frictionless pulley. And then we have dangling off the edge of the table, we have this is the load, and this is often called a block. Let's think conceptually. If I let that system go, remember this is a smooth table. It's like a bin on ice. It's better than bin on ice actually. If I let that system go, what will happen to it? Will it move? Will it stay still? Will it retire? What will it do? It will move. Which way will it move? Which way will B go? To the left or to the right? It'll go to the right. Which way will the load go? Will it go up in the air or down? It goes down. Things fall, yeah? It won't fall quite as fast as if it was just not connected. It won't fall at the same rate as a free fall object, because it's connected to B and B's got inertia and it don't want to accelerate. So this is a system where I can mess with the acceleration of the system by messing with the inertia of the system. It's a very clever designed experiment actually. It's a very clever design thing. There's going to be a force pulling back on that load. Let's call it tension. There's also, of course, the weight. Let's call it Fg of the load. Yeah? There's going to be a force pulling forwards on the block. The string's going to be pulling forward. That's also a tension. How does the tension of the string pulling on the block compare with the tension of the string pulling on the load? They're the same, because they're an action-reaction pair, actually. It's like, okay. There's a weight on this. And there's a normal force on this. What can you tell me about the size of that weight and the size of that normal force? They're going to be the same, aren't they? Because they're on the level. Is there a force backwards resisting this motion? There is no frictional force. There's an inertia that resists acceleration, but that's not the same as a force. So it's kind of interesting. I just realized we've gone for about an hour, is that right? So let me just pause here. Let me stop.